In this video, we apply the first law to an isothermal gas expansion. Okay, so in the last video, we introduced the statement of the first law, which is that all the changes to the internal energy of a system are just the balance of the energy transferred as heat and the energy transferred as work. Now what we're going to do is just use this equation and see how it plays out for a fairly straightforward system, which is the isothermal expansion of an ideal gas. Okay, so we have 2 moles of an ideal gas at 298 Kelvin, occupying a volume of 10 liters, and they are under an external pressure of 1 atmosphere, and that external pressure is constant, and that is an important detail. And then that gas is doing work on the surroundings by pushing out that piston until its volume doubles. Notice that this is a closed system, so the number of moles doesn't change. We're specifying that the expansion is isothermal, so the temperature also stays constant. And what that means is that if the volume doubles, then the internal pressure of the gas must decrease by a factor of 2. Okay, so then the question is, well, what would be all of the variables in this first law, right? So what is the change in internal energy, what is the energy transfer as heat, and what is the energy transfer as work in this particular process. Now, the only thing that we actually know how to calculate here is work, because work is, in a gas expansion, is that expression that we have right here, and we've done this before. We know how to do this, right? Now, for heat, we actually do not know how to do this, because notice that this process is isothermal, right? So we've only learned how to calculate energy transfer as heat if the only thing that is happening is the heating or cooling of an object. But of course, this is not the heating or cooling of an object, right? We're not simply adding energy to that gas here and observing a change in temperature. As a matter of fact, the only thing that is happening is that there's a gas expansion, but the gas stays isothermal, so no change in temperature. Now that does not mean that there's no energy transfer as heat. As a matter of fact, there will be energy transfer as heat. It just means that, again, this is not a simple heating cooling process, so we cannot really use that expression to calculate heat. Okay, so we know how to calculate work. We do not know how to calculate heat yet. And that means that we don't know how to tally the change in internal energy. Okay, so to solve this problem, where we have 2 unknowns, then we start to think a little bit more deeply about the process, right? Notice that a key word here is that this is an isothermal expansion of an ideal gas. And we actually know what the internal energy of an ideal gas is. From our work in the first unit with kinetic theory of gases, we said that for an ideal gas, right, there's no potential energy. Those gas particles are not interacting. That means that there's only kinetic energy. Okay, so we can say that the internal energy, which will be the sum of the kinetic energies and potential energies of all the particles in the sample, right, notice that that is simply going to be your kinetic energy, okay, because there's no potential energy. And we actually know what the average kinetic energy is from kinetic theory of gases. That is simply 3/2 RT if the gas is monatomic or there's no internal structure, and we're assuming that there's no complicated structure to that gas. This could be simply, say, argon or neon or something like that. Okay, very importantly though, what we recognize here is that the internal energy for an ideal gas only depends on temperature, right? But because this process is isothermal, which means that the temperature is not changing, that means that there will not be any change to the internal energy. Right? So automatically we know that for an isothermal expansion of an ideal gas, delta U is equal to 0. Okay, so that's how we look at this problem. Right, so now we know this, which will be 0. There will be no change to the internal energy, but there is a change, right? Notice that there's work being done, and that means that there will be heat being transferred. Okay, so what happens then is that from the work and the internal energy, we will be able to calculate what the energy transfer as heat is in this particular process. As a matter of fact, we can say that, well, this will be equal to 0 from this thinking about the ideal gas. And what follows is that then heat will be equal to minus work, okay, for this isothermal expansion of an ideal gas. Well, so the only thing that we have to then do is just calculate work, which we can in a straightforward way from that expression, and then we will be able to calculate heat and then talk about what the results really mean. Right, so let's see if we can calculate here work, okay, which is going to be fairly straightforward. Again, work is the gas expansion, so it will be the minus integral of V external differential of V from V1 to V2. But of course the external pressure is constant, okay, 1 atmosphere, and what that means is that this whole expression is simply P external delta V. Okay, that's how we calculate work in this particular gas expansion. Now, we gotta make sure that we use the correct units for this. The external pressure will be 1 atmosphere, but we have to do that in SI units, so 101,325 Pascal. And the change in volume will be in cubic meters. That is going to be final volume, V2, 20 liters, minus initial volume, V1, 10 liters. Delta V is 10 liters, but that is going to be 10 to the minus 3 cubic meters. Okay, so that is our external pressure times change in volume in SI units, and this number happens then to be minus 1.01, 10 to the 3 joules. Okay, let's do a consistency check here to make sure that the sign is correct. This sign is negative, which means that energy is leaving the system as work. And that makes perfect sense, right? Notice that is the system, that gas, that is pushing out the surroundings, pushing out that piston, and that is costing some energy to that system, right? That energy is leaving the system as work, so it should be negative. That makes perfect sense. Okay, so how do we then reconcile that with what the rest of things that we know? Notice that energy is leaving the system, right? But the total internal energy of that gas doesn't change, right? So what that must mean is that, well, if you're energy is leaving the system this way as work, but the total energy of the system is not changing, that must mean that some energy has entered the system as heat to compensate for that energy lost as work. And that is exactly what this is telling you. Right? Notice that when you do this, that is going to end up in plus 1.01, 10 to the 3 joules. Okay, so again, the way to understand this problem is say, yes, turns out that that gas has been able to do some work on the surroundings, but that has been possible because an equal amount of energy as heat has been transferred from the surroundings into the system. Okay, and overall, because the temperature doesn't change, then the internal energy of the system doesn't change either. Okay, so this is our first application of the first law of thermodynamics to a fairly simple system, which is a gas expansion. And then what we do from now on is continue to look for applications of this first law as we look to better our understanding of thermodynamics.